I see.
Yes,
I see. Okay,
we,
just
we,
started.
we just have a new semester this. Yeah, yeah, yeah.
Oh, okay. So this is because you are running a no. Then that means you're running a 3-semester system.
2 semester. We started
2
in
semesters.
February until June, and then end of August until January.
So today this is I think you told me it's a whole range of students. Am I correct? Undergraduates, graduate students, mixture.
Yeah. Today we have student. I can check from the list. Let's say we have student from material science and engineering. We also some student from chemical engineering, chemistry, and environmental engineering. Even from engineering, physics, and art. I think yeah. Yeah, because we opened this lecture for internal ITB. Yeah, last time I think it's around 50 students apply for this lecture. So hopefully no one forget to join in. So I think maybe we can start right now. Okay, so can you hear my voice, everyone? Okay, okay. So, Assalamualaikum warahmatullahi wabarakatuh, and good morning, everyone. Yeah, maybe first of all, I would like to thanks for my colleagues here, and also student and all participants who joining today's ITB online lecture. So, maybe I need also to introduce myself. My name is Lia. I'm from Material Science and Engineering, and I'm pleased to be the moderator for today's session. So it is honor for us to have Professor Ang Ki Wei as our distinguished speaker for today lecture. So we'll have a lecture entitled Waste Valorization as the Strategy Towards Sustainable Material Development. So maybe first of all, I would like to briefly introduce Prof. Ang. Yeah, I also share your CV to our student. So I will just give a brief one. So Professor Ang is a professor and chair of the School of Material Science and Engineering at NTU Singapore. He also serves on the technical committee on nanotechnology under under Enterprise Singapore, and also faculty researcher at the Skin Research Institute of Singapore. And in 2025, Prof. Ang was elected as an academician of the Asia Pacific Academy of Materials. So congratulations, Prof. Ang, for this award. And maybe I would like to highlight about the research. Prof. Ang worked a lot in the field of biomaterials, especially for food and agriculture, healthcare, and also consumer products. And I think Prof. Ang already worked for almost 25 years. And Prof. Ang also is very well known for his work on the keratin-based material. So maybe that's for the introduction. And maybe let's move to our main lecture. I would like to invite Prof. Ang to deliver your lecture. I think we will have like 40 minutes for the lecture, and then after that we will have a Q&A session. So please, Prof. Ang, the floor is yours.
Very much. Thank you, Lia. I think it's a pleasure to be here. I'm sorry that I cannot be there in person, which was originally my plan. But nonetheless, I hope this lecture will be useful to everybody, and I look forward to some fruitful discussions at the end of it. So I think as Prof. Lia mentioned, I am from the School of Material Science and Engineering. I'm also affiliated to NURI, which is a institute that is focused on environment and water research, and of course, Skin Research Institute of Singapore. I would start with very brief introduction of the university and my school. Right? This is just one slide to show you the numbers of the university to give you an idea of the scale of NTU Singapore. I suspect it's in terms of people, right? We may not be as large as some of the largest universities in Indonesia, I think, but basically we are one of the two largest university in Singapore. In terms of land area, actually, we are one of the largest. We are the largest, actually. So we have all these colleges, as you can see at the bottom, and College of Engineering is certainly our biggest college, and my school, Material Science and Engineering, is one of the schools within this college. As I mentioned, we are one of the largest in terms of campus size. And so for those who have visited NTU before, Leah and others, I see Saifu is here as well, right? So those who have come to us before will recognize all these buildings that we have, some of the more iconic buildings in NTU. And here you have an overall view of the entire NTU campus. So we sit on 200 hectares of land, and this is the largest university campus in Singapore. Probably 200 hectares again is nothing to Indonesia, right? But for Singapore, 200 hectares to one university is a very big deal. So we're quite happy with that. And we still have land area to expand for future needs. Coming to the school itself, so I've been with the School of Material Science and Engineering for 17 years now. Just to introduce again the size of what we are, right? If you look at these numbers, so in terms of student population, we are about 1,000 all the way from undergrad to graduate. Actually, this makes us probably one of the largest material science and engineering schools in the world. Maybe only some in China are bigger than us, but so we're actually very big for a material science and engineering school. 47 actually now faculty members, right? And we operate a lot based on research funding that are externally won. So this is roughly our 5-year research budget. We focus a lot on technology translation. So a lot of my research that I'm going to introduce today are also very application-driven, translation-driven. And so besides the usual papers, of course, we actually emphasize quite a bit on technology translation. So we encourage our people to develop a lot of technologies that can be patented, right? Especially so in terms of IPs and of course in terms of company spin-offs. This is something that we hope can set us apart from some of the materials institutions across the world. So very briefly, these are the research focus areas of the school. And you can see that these areas are very are grouped based on technologies, right? So technologies in energy, in harsh environments. Today I'm going to talk a lot about biomaterials, quantum, and AI certainly, right? These two are very important upcoming areas, and definitely materials for environment sustainability, right? So this is also part of the focus of my talk today. And we are supported actually, sorry, I don't have that part. So basically we group ourselves based on these research focus areas instead of the traditional material types. Because today, as we know, right, many technology sectors make use of multiple material types. So we don't divide ourselves based on material types, but we divide ourselves based on technology sectors. Right, so that brings me to today's topic, right? We want to talk about waste valorization, and we want to do waste valorization because of sustainability. Right? So this is a figure put together by one of my students in this review paper that we published not too long ago. Key considerations that you have to make if you talk about if you want to talk about sustainability in materials, right? So certainly the raw material that you're using need to be abundant, hopefully renewable. You need to consider, of course, safety issues, processing issues, certainly properties, all kinds of properties, including mechanical properties, barrier properties. If you talk about biomaterials, then degradability, of course, and any level of customization that is possible. I think typically only when all these are satisfied, then you can potentially develop that material platform into something that is truly sustainable, right? So it is on that basis that that we started on a journey of looking at how to valorize waste. So waste, of course, can come in very many different forms, right? So today we are focused a lot on nature-derived biopolymers because I think in my group we want to try and minimize the creation of new materials, right? So we want to use any kind of existing waste materials that are either intentionally or unintentionally produced anyway, and convert them to something that is of higher value. And that's why I'm choosing, these two raw materials for today's talk, cellulose and keratins, because these are materials that are already being produced in society for various reasons, either for food production, or natural processes such as human hair, of course, feathers as well because of food production. I think a key important point that I want to bring up also is that waste valorization, right? The word valorization I think is very important because if you just take certain waste and convert it into another useful material that is not of very high value, then you have the challenge of commercial viability, right? To make it economically viable, so that companies, industry will uptake those technology, then it is important that the new form of technology that you develop has much higher value compared to its original use, right? And that's where valorization is a very important consideration here. So let me start with cellulose, right? And specifically cellulose in food. So I think it is not a new concept, but over the years, people have shown that using cellulose in food, especially nanoscale cellulose, has very interesting outcomes, such as these examples quoted here. These are not from my group, right? These are work that has been done by other people over the years. So we know now that nanoscale cellulose can be a very efficient stabilizer and emulsifier in food products. So you can see, for example, this top right picture showing that if you add nanoscale cellulose instead of microscale cellulose into some kind of emulsion suspension, right, then that emulsion is very stable. So applications such as milk and yogurt becomes a very interesting possibility there. If you have some level of these nanoscale fibers in bakery products, for example, right? You also see that you get potentially bread that is fluffier, softer and better in terms of texture and so on. So people like that. And if you put them into meat such as patties, right, then people have shown that a small amount of this kind of addition actually keeps the patty more juicy. So it retains the oil, retains the fluids in the burger, in the patty better. So again, it's talking about texture and improving basically the consumer experience, right? So there is some interesting ability that nanoscale cellulose can actually offer in terms of food. And so this came from collaboration with HSPH, which is the Harvard School of Public Health, quite a few years ago, where we thought that maybe it is possible to use nanoscale cellulose for other kinds of functional outcomes in food as a food ingredient. So we took different forms of reference materials that they have, right? So the nanofibrils with the F in front, or the basically more short length crystalline version of the cellulose, or nanocrystals, right? So the difference between these three are really more on the scale, right? The length scale and the diameters of these fibers. But basically, we are very interested in using fibrillated cellulose, nanoscale cellulose, as shown in this SEM picture on the right, for some functional food outcomes. So the most immediate application that we think would be interesting, right, is to use this nanoscale cellulose as a food moderator. Moderator meaning that it can possibly actually moderate how certain food ingredients are being digested and absorbed into the body. So to do that, we set up a GI tract simulator. Actually, this was done over at the Harvard School of Public Health, where we basically, through their earlier work, we developed this simulator, which includes the mouth phase, the stomach phase, and the small intestinal phase of sequential digestion of any kind of food material that you may put into this sequence, right? But I have to say it is still a manual simulator, so you still have to manually transfer the food and the digester from one phase to another phase, right? We haven't gotten to the stage that we can somewhat automate this, and some others have actually developed some automated GI tract simulators in other places, but we have not done that yet. So in this study, we use the manual way. I think what was interesting for us is that, we wanted to look at how nanoscale cellulose actually moderate the digestion and uptake of lipids, specifically of triglycerides in food. So the idea or the hypothesis back then was that because of the unique features of nanoscale cellulose, right, we think that these materials can actually reduce the digestion and also subsequently the uptake of fat by actually changing how these fats are being digested, how the triglycerides are being digested into free fatty acids. So to do that, we rely a lot on the pH stat, right? This is the setup in the small intestinal phase, right? After the small intestinal phase digestion, where we expect the lipases to be acting on the fats, we take out this material and run them through the pH stat to actually work out how much basically sodium hydroxide we need to neutralize the fatty acids that is being produced. So more NaOH being used means that there is more fatty acids that were produced from the digestion of triglyceride, right? So if there is successful moderation of fat digestion, it means that you will have less free fatty acids present, which means you will need less sodium hydroxide to neutralize the digester. So that's the idea, right? So indeed, when we run this experiment, we saw that as you increase the amount of nanoscale cellulose, and especially if you change the cellulose from a micron scale, right, a type of cellulose into the nanofibrous scale. So you can see anything with N inside refers to nanoscale fibers, right? You see that the level of NaOH you use starts to drop, which means that there is a reduction in the production of free fatty acids. So if we translate that into a quantitative bar chart on the right here, you see that these three groups, right, using nanoscale fibers, you get always a reduction in the amount of free fatty acids produced compared to the microscale fibers and compared to the existing commercially available dietary fibers, such as dextrine, such as psyllium husk fibers. So that was an in vitro study that was very encouraging to us, suggesting that without knowing the mechanism yet, nanoscale fibers seems to be able to reduce the amount of fat digestion in the gut and therefore reduce the amount of free fatty acids available to be uptaken by the body. And with that, we went on to do an in vivo study in rats, right, where we fed these animals with high-fat cream and high-fat cream in the presence of nanoscale fibers. So to cut the long story short, basically we fed these animals with these materials, and over a period of time we tracked the amount of triglycerides in the blood, right? So if the free fatty acids was successfully digested and uptaken by the body, they will be transformed back into triglycerides and transported in the blood system. So therefore, if you track the amount of triglycerides in the blood, you also get the direct correlation to the amount of free fatty acids that the animal actually absorbed. So we saw that after 1 hour of feeding, you see that there is a very significant reduction in the amount of triglycerides in these animals compared to the control group, which also fed the high-fat diet without the cellulose nanofibers present. So that was the important outcome of this study, right? Basically, we were able to reduce the triglyceride levels in the bloodstreams of these animals by about 36% by adding only about 1% of nanoscale cellulose fibers, specifically the fibers that are in the range of 50 nanometers. When we add this to the food, when we add this as a food ingredient. So that's the work that was published in this paper, ECS Nano. So we dig a little bit deeper into this, and we visually, the most obvious thing we saw was that in the presence of the nanoscale cellulose fibers, you can see that at the small intestinal digestion phase, you get what looks like little lipid droplets, because they are perfect spheres, right? So we know that these are very likely, right, these lipid droplets, because of the behavior of the lipid in that particular environment, and they are mostly chelated along the fibers, which are the cellulose here in this case, right? So that suggests to us that the presence of the nanoscale fibers actually is able to trap the fat in the form of small little lipid droplets within that particular system. And we did some molecular simulation as well, which is the data available in this paper if you're interested. But basically, overall, the proposed mechanism we have is that this is a very physical process, right? Where in the presence of the nanoscale cellulose fibers, you get like sequestration of the lipid droplets, as what you can see here, almost like a bunch of grapes, right? And in that situation, you also have separation of the lipases, the proteins, and the bile salts that are sequestered onto the nanoscale fibers. So basically, it means that your enzymes and your coenzymes and your bile salts actually don't come together on the lipid droplets. So if they don't come together, they will never get digested. Right? So if they don't get digested, you don't get fatty acids, and therefore you don't get uptake of fatty acids as well. Which means that this lipid droplets gets passed out from the body as fats, right? As lipid droplets, but it is not an excessive amount of passing out through the stools, right? Because you can moderate this. And in our case, in the animals, it is about 36% reduction. And so it's not like 100%, passing out of the fats that you take. Which actually I forgot to mention, if I go back to this chart, right? If you look at commercial products available, like this one on the extreme right? This is Orlistat. This is a commercially available off-the-shelf lipase inhibitor. So this is sold as a weight management drug, basically, right? So what this Orlistat does is that it completely blocks the activity of lipases. So there's completely no digestion of fats, but which means that 100% or near 100% of the fat is being passed out in the stools. That is actually a big problem for consumers, because you have greasy stool problems, you have flatulence, you have discomfort in the gut system, right? Which is not what consumers want. So by turning to something like the nanoscale fibers, it is possible that we can do this in a way that is not so excessive, that can be moderated, that you don't result in this greasy stool problem. So that's the cellulose story as one example of valorization. I'm going to quickly move on now to the second part of the story, which is keratins. And this is a material that I use a lot currently in the lab. I use hair keratin as an example here, but actually keratins are a very highly conserved family of proteins that are present across many species of animals, right? Including chicken feathers, including sheep's wool, and so there are a lot of similarities. But basically, using hair as an example, right? These keratins have certain interesting features. For example, they have very well characterized isoelectric points. We know that they form fibers naturally in the body. They are obviously highly abundant, and other people have also shown that they are biocompatible, bioactive, and so on, right? And so this is the source of material that different kinds of purposes. I will just focus on this part here, which is that, in our lab, we use a reductive method to actually extract keratins, whether it's from hair, whether it's from feathers. Always use a reductive cysteine molecule. And the reason we do that is so that we can keep the thiol groups active we can find ways to keep the thiol groups active so that we can use it to recombine either with other materials or recombine with itself to form back organized structures, right? So that is the background behind what we do with keratins. So this is a very early example where we took this, in this case, hair keratin, simply bring the isoelectric points of these keratins are between 4 to 7. So there comes an interface, right, where when a critical pH value where they start to come together and gel. Right, so that's what we observe in this particular study, a very early study that we did in this space. And so we know that keratin has a natural ability to form hydrogels, and these hydrogels are actually capable of allowing cells to grow in them. And interestingly, they are also less degradable than collagen, so they don't degrade as fast with proteases, and they are fairly biocompatible, right? So this is what we have shown in earlier studies, and that was a gel form. If you take that gel and let's say do other kinds of chemistry onto them, in this case we conjugated with alginate by forming this excuse me, by basically cross-linking using the classical EDC chemistry, right? NHS EDC chemistry to form new peptide linkages between the keratin and the alginate. You get very nice and mechanically stable sponges like this. In our case, we show that if you subcutaneously implant this into animals, in this case, black sex mice, you see that there is nice infiltration of this tissue and nice growth of blood vessels within the material over a span of 2 to 4 weeks, which is not necessarily the case even for collagenous product like this one, right? This is Pelnec. This is actually a porcine collagen that is used in some hospitals all over the world. And then we dig deeper into the mechanism. We dig deeper into the understanding of how these keratins assemble, and we found that there are possibilities to induce these keratins to self-assemble into nanoscale fibers outside the body by controlling pH, by controlling salt concentrations, right? So here, I think I'll zoom into just this bottom right image here under the TM that shows that in some conditions, you get pretty regular and pretty nice nanoscale fibers that looks quite consistent, right? So it means that once you take these proteins out of the body into a petri dish, if you give it the right conditions, it is possible to induce them on their own to just self-assemble into regular structures like this, right? And if you find ways to assemble these regular structures together in the bulk materials, which can become useful, right? Of those studies, right? So here's one example where we encourage the self-assembly process through a freeze-thaw method, right? This freeze-thaw method is also not new. It's not invented by us. We just adopted freeze-thaw methods that others have used, but we use it for the first time on keratins, right? So we show that this freeze-thawing method does encourage these proteins to come together to self-assemble, and you can get sponges like I show here that is pretty resilient, and you can squeeze out all the liquid that they absorb in a quite harsh mechanical way. Once you put it back into a liquid medium again, it's able to reabsorb that liquid and actually swell up to its original shape and size. So this suggests that this can be an interesting material that we use for various biomedical purposes. And if you push that further, right, if you do that freeze-thaw strategy using a directed ice crystal growing manner, what we call directed ice templating, then it's possible to create these long channels in terms of the micropores that are created within the sponges. So this is one strategy that we're trying to develop further and use it for medical applications such as tendon ligament repair. But we have not done those studies yet. Here is a demonstration of the possibility of creating microstructures like this. I will just skip through this very quickly. Basically, you can combine the keratin with other materials such as dopamine, right? And you start to leverage on existing known mechanisms of oxidation between keratin and other materials to create strain stiffening materials like this one, where you can get exceptionally high elongation and strain rates, so that you can maybe adopt this for specific biomechanical purposes. The more recent development that we've done, I'm going to spend a little bit more time, right? So this one is on fibers. So we recently, with my student Laura, who is graduated now, right? So using this method of IPC, interfacial polyelectrolyte complexation, where you put a polycation and polyanion together, allow them to interact, right? And this forms a physical solid interface, which you can then draw to form fibers, right? So that's the broad idea of IPC method to form fibers. So we can adopt keratin to be, positively charged or negatively charged, and in this particular study, right, we combine keratin onto itself, or we combine the negative form of keratin using positive cation chitosan, which is another naturally occurring biopolymer. And if you focus on this video now in the middle, I hope you can see this. You just bring two droplets together using a pair of forceps, right? You allow them to touch, they form an interface. You can then just simply draw out the interface in the form of a fiber, put it on the rotating mandrel, and you can now start to spin fibers, right? Slowly, the mandrel rotates, and the fiber is continuously being drawn, right? You can see the fiber is continuously being drawn from the middle, just simply at the interface of these two droplets. So again, this requires quite a fair bit of optimization and controlling of concentration, pH, electrostatic conditions, certainly the speed of drawing, etc., right? So once you get all that conditions correct, it is possible then to start drawing such fibers continuously. And you see on the right, this panel of SEM images, right? You can get pretty nice solid fibers as shown here. And again, mechanically, some of these fibers are robust enough. You can tie knots, you can do braiding, etc. So that immediately gives us the idea that you can use such fibers as sutures, right? So that is the application that we're using this for. Just very quickly, in terms of characterization, we actually found that, there is appearance of biofringence inside these fibers. So, using classical methods of wide-angle XRD, congruent staining, you can see that there is some level of actually stacked beta sheets, which means that there is amyloid structures within these fibers. We characterize the mechanical properties to show that they are actually not too far away from commercially available sutures. In this case, we compared it against polyglyconate, which is a commercially available suture that is made from polycaprolactone and polyglycolic acid. And of course, we have to try this out, right, on a real scenario. So we tested this out on incisional wounds in mice. And here on the left, you see Laura actually demonstrating, on a piece of cadaveric skin, that this material can be used as a suture to close a simple incisional wound in the skin. So on the right, you see then images of these wounds that heals over 7 days, and the wound site actually heals quite well. So again, this particular demonstration on the left, right, is a pure keratin material. So it's keratin on keratin. And you can see that the material is actually strong enough for you to tie a knot and tighten the knot for this particular purpose. Right? Yeah, so that is the study that we did. And of course, we are very particular, and we have to be very particular in terms of the immunogenic reaction, right, that this material may cause. So we did a separate study to specifically look at the immunoreaction. So on the left, you see this polyglyconate suture that I mentioned just now. So this is the commercial one, right, that is currently used in the clinic. The one in the middle is a combination of chitosan and keratin. The one on the right is the keratin on keratin fiber. So at a glance, you immediately see on the top image that the chitosan one is not performing so well because you've got quite extensive level of fibrosis around the suture. But the keratin one is actually doing very well. So the keratin, the level of fibrosis you see here is very comparable to the polyglyconate one, which is the level of immunogenic response that is expected and actually accepted, right, by the body. So that is for us very exciting. And the right panel shows further mesentericrome staining. So this actually not quantifies, but actually stains the amount of collagens, right, that is around this suture that correlates to fibrosis. We also see that the keratin one is degrading. You can see the original pretty much circular cross-section has become irregular shaped. This is only after 21 days. Unfortunately, we couldn't do a longer study for this particular round, so we stopped at 21 days. But you can tell already that there is some level of degradation. So going forward, we would like to study this more to understand in this situation, how long does it take this fiber to fully degrade. Polyglyconate, for example, is known to degrade in the body after 3 months, sometimes even after 6 months, right? So it's a degradable polymer as well. So that is a suture application based on fibers. The next one I want to talk about is a hydrogel, but an interesting gradient hydrogel. So this is done by my other student, Marin. So I mentioned the usefulness of thiol groups in the keratin, right? So these thiol groups are known very well established in the literature to be very strongly capable of binding metallic ions. And we decided to try that out with silver because silver is a very useful and important antimicrobial agent that is clinically approved. But silver has its problem, right? Because if you have too much of it, then you can potentially lead to silver toxicity. So one way of preventing that or minimizing that is to make sure that silver is released in a controlled manner. But silver itself can become a cross-linker in our keratin system, right? So that gives us an idea. Can we then use silver to cross-link keratin itself? And then as the keratin degrades, the silver is being released to become an antimicrobial agent. So it's like a 2-in-1 function of using silver. So Marin experimented with this and showed first that it is possible to indeed get, very quickly gelling material just by injecting keratin into a bath of silver ions. So you get injectable hydrogels, right, as shown in the bottom right. That itself is not very interesting for us. What can we do more with this, right? So what Marin has done is to devise a way that you can actually layer a film of keratin onto a silver bath and have that layer of keratin form an interface between the silver and the keratin, right? And when that interface is achieved, then you have slow diffusion of silver ions from the bottom upwards, as shown in this cartoon, right? And remember, as the silver interacts with the keratin, it will cross-link it. So as the silver continues to diffuse upwards because of the concentration gradient, right? The keratin will continue to gel further and further up, right? And so it forms a gradient. So this video in the middle will demonstrate that, where you drop a layer of keratin onto silver, right? It forms a solid interface immediately, a slightly lighter brown color you can see there. That's the interface. And then you leave it there like that. And if you continue to add more silver on top, then you have if you continue to add keratin on top, you have silver continuously diffusing from bottom up to form an entire gel. So here, this top right image shows a series of different hydrogels of different consistency by varying thiol-silver ratio. So we did the XPS studies to show that indeed at the bottom of this hydrogel, you get the appearance of sulfur and silver interaction. So that's the thiolate silver interaction that actually does the cross-linking. And this is actually not present in the top of the hydrogel, where the silver is not present, right? So you can control how much the silver goes up, but it still gels because of the keratin-keratin interaction. Yeah, so by doing that, you actually get a gradient hydrogel. I think in the interest of time, I will skip some of these details, but to show that we can actually track the gel front. And here, indeed, if you look at this SEM, this is one continuous gradient that you can achieve, right, using such a method. And the interesting thing about this is that gradient is continuous, right? It is possible to create gradient hydrogel by layering systems. But here we don't use layering, we use diffusion. So that actually produces a continuous gradient, which is not very common in the literature today. So of course, the potential application is actually wound healing, right? By using silver as the antimicrobial agent. So we showed that the antimicrobial agent is working, right? It does release the silver to kill bacteria, and there is in fact encouragement of production of some of these ECM molecules as well. And if you implant this in vivo, you do see, not very significant to be honest, but you do see that in the silver basically gradient hydrogel system, right? You do get an increase in production of collagen in that wound setting when you use this material as a hydrogel to regenerate the skin, compared to just JAMA, for example, or when you don't have anything. So that's interesting for us and something that we are continuing to explore. Yep, and so this was published in Small. So that is kind of a very quick summary of the bio applications, right? I hope to spend the last 5 minutes maybe just to quickly talk about an interesting development that we are doing now as well that is outside the biomedical space, but suggesting again, right, the potential of valorizing a material such as keratin, and that's food. Right? Something still very human related, but it's not biomedical, right? I would just quickly say that in Singapore, we have a terrible situation with food, right? Because we don't have land, we need to depend on imports, including from Indonesia, a very important partner for us to bring us food, to supply us enough food. We want to try and figure out ways that we can increase food production and increase food production in a sustainable way, right? That is very important. And so we have this Singapore Green Plan that we want to develop sustainable solutions, and we want to be able to produce a certain amount of nutrients that we need within Singapore making use of technology, making use of urban farming techniques. So what has that got to do with my keratin stuff, right? So when you talk about urban farming, then you need to think about using systems such as soilless culture systems, definitely, right? So we're talking about hydroponics, we're talking about aeroponics. In those systems, you always need to use a growing media, basically a growing media that will hold your seeds to allow the roots of vegetables to anchor. And currently, materials used include things like polyurethane, rock wool, or peat. Right, we get a lot of cocoa peat as well from Indonesia for this purpose, but this is not sustainable at all. All these materials are not sustainable, right? So basically, what we want to do is to see whether it is possible to adapt keratin into these sponges that we can use as growing media for growing crops. So that's just that simple idea, right? But then the question, what's the big deal, right? So why use keratin? I can use many other materials to make sponges that I can use for growing crops as well. What is interesting is that besides making the sponges, the keratin themselves, again, because of the chemistry, right? Because of the naturally occurring thiol groups, I can conjugate many types of nano agrochemicals. So we're talking about metal ions, right? Many metal ions, calcium, iron, zinc, molybdenum, for example, these are all important micronutrients to crops. And currently, these ions are being circulated just in water, right? And fed to these crops. A lot of these are actually wasted, lost in the environment. So if we can conjugate some level of these micronutrients into the sponges, then we can effect targeted delivery. Just like drug delivery to the human body, we can do targeted delivery, controlled release of ions to the crops. Right? That's the whole idea. So we've done this now with hair, with feathers, with carpet, wool, right? I mean, our local agency tell us if you use human hair sponge to grow vegetables, I think the public would not like that. Right. So we decided that for crop growing purposes, we are using mostly chicken feathers. So here again, you see that we can make sponges that are very highly water absorbent, highly mechanically resilient, right? Highly porous, certainly. So this protocol has to be a bit different from what we were using for the biomedical applications. And in our early studies, we show that yes, indeed, these material themselves do release nutrients to crops. In this case, we use Arabidopsis as the model plant. This is our very first plant study, actually, a few years ago. So you see here on the top left, commercially, when you grow, sorry, not commercially, when you grow this in a material that is commercially used today, the plants don't grow so much if you use only water. All the other groups you see here are based on keratin materials. Again, if you use only water, the plants survive, they germinate, they grow seedlings, and you see actually nice production, nice growing of the leaves, right? Which you do not see when you use a commercial sponge that has no nutritional value. So we've gone on to try many things now, and one of our studies also show that this is a commercial crop, Naipai. I think it's definitely available in Indonesia as well. Basically, we grow them in polyurethane foams versus we grow them in keratin sponges, and we show that indeed, in terms of shoot length, in terms of biomass, in terms of both wet and dry biomass, you see a significant increase in those crops grown in the keratin growing media compared to the polyurethane foams. Okay, I will skip through this. Basically, we are trying to do this now in a more large scale setting, right? And you can see we set up this research facility where we can track the growth of these plants using a lot of data. And basically, we build cameras on top, we have sensors at the bottom, and just very quickly to show you that when the system is running, it looks like this. We have cameras on top, you have sensors below, and we're trying to track how the plants behave over time, and we're going to collect a lot of data and hopefully use data analysis methods to develop some AI tools, in fact, right, to help us determine what are the best conditions to grow some of these crops using the sponges that we produce, right? So that is the next phase of this particular project. I would just say one outcome that we can foresee out of this, right? So here we profile the biochemical analysis of some of these crops, so bayam and kailan, right? These are two common vegetables in this part of the world as well. I just give you one example, right? Here, highlighted in this red box, you can see that if you supply nitrogen over a concentration gradient, then typically farmers will choose the conditions here that gives them the best dry weight, right? Because farmers always like to grow crops to be bigger and more, right? Because it means more money for them. But if you look at comparing these to, in this case, potassium content in the crops, you see that potassium is highest, right, within the group that has smaller biomass, which means that the plants look like they are smaller, but the nutrient content is actually higher, right? So what we hope to achieve is that by changing how we deliver nutrients to plants, you may potentially produce maybe, right, smaller looking kailan, smaller looking bayam, which to the farmer is like, less weight, but they earn less. But actually nutrient is higher. So they can potentially still sell this at a higher price, even when the crops looks smaller. Right, that's one of the stories that we're telling that is potentially possible using this approach. Yeah, so I think with that, I just want to close off by saying that we have these two examples that I've given today, right, in terms of using cellulose and keratins as waste streams, nature-derived polymers, but very versatile in terms of biochemical properties and what you can do with them, what you can engineer with them. And these are two examples how we can potentially truly valorize waste, right, for different purposes that is applicable to society's needs. Yeah, with that, thank you very much for your attention. And of course, I have to thank my group members and all the funding sources here from Singapore. Thank you very much.
Thank you so much, Prof. Ang. It's very insightful talk. So maybe we will move on to the Q&A session. So anyone that would like to ask something, you can raise your hand. Maybe just type on the chat box. Yeah.
I guess feel free to type, feel free to also ask, totally fine.
So anyone from the audience, you want to ask something? So maybe, it's very nice lecture from, especially me from materials engineering sometimes. Oh, Arkan first, okay. So please, Arkan.
Hello,
Yeah.
Yes.
is my voice clear?
Yes,
Yes.
yes.
I think I quite interested in the beginning of the presentation when Prof. Ang mentioned about food engineering, I guess, that can make bread fluffier and another thing. My question is there any specific research or major in NTU that apa ya that research in that part in the topics, and what
Then-
else can maybe and I mean can the research being used in the industry or is already used? Thank you.
Okay, so I guess the question is, are there such research in NTU, right? That's the first question. Second is whether this has been used commercially. So as I talk, I just go to the front. So the examples I show on cellulose, right, on using in bakery items and so on, right? This is just want to qualify. This is not our research, right? You can look up this paper if you're interested, that describes how what are the potential outcomes when you include nanoscale cellulose in food items. Okay, these effects are there only if the cellulose is used in the nanoscale, right? Nano in terms of the fiber diameter, right? So we know that micron scale or natural dietary fibers are already used a lot in food, correct? We know that high fiber diet is healthy for various reasons. We have all kinds of high fiber drinks, right? You can buy sachets of psyllium husk fibers, for example, and make a drink and just drink it, right? So all these are already available. The question now is, if you only use nanoscale cellulose for the same purpose, then what new effects can you bring, right? Which is what these studies have shown and what our studies have shown, right? But the problem is that once you have a nanoscale food material, then you have some concerns with regards to safety, right? So regulatory bodies all around the world are not very clear yet how to regulate nanoscale materials in food. Even though nanoscale fibers, nanoscale cellulose probably are already naturally occurring in our food system, right? When you eat vegetables and let's say you grind up the vegetables, you chew the vegetables a lot, and then you eat them, I believe a certain percentage of those fibers are already nanoscale. The problem is that from a safety regulation point of view, right, if you intentionally add a nanoscale fiber into food, then the question is how to regulate that. So that part is currently missing. And so actually, what I know is that no country in the world has actually approved the use of nanoscale fibers in any food item currently. Zero. But there are already food items out there, right, that claim that they have fibers, sometimes in the nanoscale range, that are present in their food items. It can be supplements, it can be anything else that has certain effects. Right? Some of these are already being used. They just don't claim that they have added nanoscale fibers. Yeah, so there is no clear answer for your second question, right? Just to say that, officially, none of these are approved yet. Yeah, but practically there's already some use in this. So in NTU, we do have people working on things like this, right? This is not just in my school, but also in our School of Chemical Engineering, right? Chemistry, Chemical Engineering, and Biotechnology. We do have this kind of work all across the campus, yes.
So Arkan, it's already you get the answer, Arkan. Do you have any other question? Hello, Arkan.
Hello.
Yeah.
I think it's enough. Revi already raised it.
Okay.
Thank you, Prof. For the answer.
Thank you.
Okay. Then we have one more question from Revi. So Revi, please.
All right, so thank you for the insightful material. It especially relates to my study on silver nanoparticles, but I heard about health when talking about the food part, and with the rising concerns on ultra-processed food and the market need toward real food, can these nanocellulose additives be ensured to have safe processing that won't be as scary as ultra-processed? Thank you.
Yes, actually, I believe so. There is already an existing industry of producing food grade cellulose, but not in the nanoscale. Right? So I think that is already approved. So if you look at, for example, FDA's list of GRAS material, right? GRAS is generally regarded as safe, GRAS. Microscale cellulose is actually there, which means that today, if you buy, commercially available bulk cellulose or microscale cellulose, and you add it to your bakery products or you add it to yogurt or whatever, it is totally okay, approved. Of course, you must use food grade, right? So I don't think it is a challenge to also develop the industry that can supply nanoscale food grade cellulose for food purposes. Right? The only challenge is that the regulations the rules around regulations must advance enough to say that, okay, if you satisfy this, then the nanoscale cellulose can be approved. That is what's missing currently.
Okay.
All right, thank you.
Yeah. So maybe one more question, Propong, is okay?
Yeah, sure.
Any other question? So maybe from me, maybe one question, last question. So yeah, because in Indonesia is sometimes, yeah, we know it's difficult to do research in the field of biomedicals. So that's why we try to switch a little bit, let's say, to cosmetics, something like that. And so maybe you have yeah, insight about can also we use these keratin materials to be, let's say, yeah, apply as a cosmetic materials in maybe in which area? Yeah, so yeah, very yeah. That's a big. I think me maybe this is Bu Eka also same, working with biomedical here is quite complicated. So that's why I think cosmetic one is much more potential.
Yeah, it's the same challenge that all of us face, right? All of us working on
Yes.
biomedical face. I have the same challenge, definitely. So the example I gave, right, sutures is a little bit more advanced, right? Something else I didn't talk about is films, right? Keratin films that can be used as a cell carrier. But to bring that to real clinical success is a long way, and of course the regulations is a problem itself as well. Some things I didn't talk about, coatings, right? So I talked about the nanoscale fibers and the coatings. So you mentioned cosmetics. I think that's quite interesting for us as well, because today there are already commercial products, for example, hair products, right? I think hair is the most obvious. All the conditioners and shampoos, some of them already contain keratin.
Yes.
Right? But the general public have absolutely no idea what the keratin is doing, right? In the conditioner or the shampoos. It's just like putting collagen on as a skin cream. people also don't know what the collagen is doing, but collagen is in skin. So if you put collagen in the cream, it's probably better. So same thing, right? Keratin is in hair. So if you put keratin into a moisturizer, it's probably good for your hair. So I think one of the way forward is, can we really properly work out scientifically what form of keratin, what does it do actually on the hair, and prove the mechanism, right? Prove the mechanism to relate to the function. I think that would be interesting. So I think keratin as a coating on hair could be very interesting there. Keratin as a coating on skin can be very interesting too. But the question is what angle and so on, right? At the moment, I'm not really working in that space, but it's something that you could try and, of course, work on as well. There's one other angle, just very quickly, which is the pigment, right? So in doing the keratin, in extracting the keratin, we also extract the pigment from hair. So these pigment are natural UV blockers, right? This is Mother Nature's solution. This is Mother Nature's sunscreen, basically, right? So we are trying to use this material now as a sunblock agent in creams. That is something that we are trying to do. So that is kind of cosmetic related as well. Again, using a natural UV blocker.
Okay, thank you so much. Maybe one more from Bu Eka. I think you
Yeah.
already know her. Bu Eka, please.
Sorry, I think the time is up, but I still wonder one more question. Is it okay, Prof. Ang?
Yes. Okay.
Yeah, please introduce myself. My name is Eka. I'm also received Inspirasi program. I bound to Professor Dalton there. So
Nice.
I also work in biomaterials field, and yeah, I have one more question related to keratin-based biomaterials and probably cellulose-based biomaterials, since it is also regarding to the food industry. So, do you perform any immunogenicity and potentially allergic reaction tests to discount this kind of biomaterials? Because I think that kind of testing also important to be used as the biomaterials application.
Short answer is yes. So the most basic let's say allergenic or skin toxicity tests, maybe I don't have that here, is metabolic assay, correct? The MTS, MTA assay, that is the most basic, and that is one of the ISO standard, ASTM standard as well. So I think that is the easiest, and we've done that, right? Basically to check whether when you add this material into your cells in culture, do you get highly elevated or reduced level of metabolic activity? Right. And then you put in your positive and your negative control. As long as it's within the allowable range, then you conclude that the material is, let's say, non-allergenic or non-immunogenic to skin, in my case, right? Or of course, we do studies like this to look at the immune response in the tissue, right? But this is still not in-depth enough if you really want to eventually move this to the clinic, right? You have to do your immunogenic test based on profiling the immunoglobulins, for example, and also the blood cells, right? You got to profile the neutrophils, the macrophages, and so on. So those are more downstream to really look at immunogenic activity. What we have done is a tissue level fibrosis, looking at this, and of course looking at macrophage infiltration as well. So here on the right, is a panel showing the level of macrophage infiltration into the site. But in my group, actually, in these platforms that I showed, we actually have not gone on to look at immunoglobulin profiling. I think that is the next level.
I see. Thank you for the answer. Very nice talk. Thank you very much.
Thank you. So I think that is the last question from the audience. I think maybe some still have some question, but I think we have to end the session. So yeah, Prof. Ang, thank you so much. Yeah, I know you have another meeting after this. So I think we have reached the end of the QA session, and yeah, once again, we have a very nice lecture today. We very appreciate your present in this lecture. Hopefully, one day you can visit us, Nai TV.
Yes, I definitely look forward to that. Yes.
Yeah, because I also heard that ITB now would like to increase the collaboration. Maybe some people will visit NTU in a quite close time. So again, thanks again. And
Yes, thank you. Thank you as well. Thank you very much for having me here. I apologize again for not being able to come, but I definitely would like to find a time to come and visit and have more interactions with you, yeah, and also the students. Yeah, and of course Saifu again, right?
Okay, thank you so much, Prof. Ang, and
Okay,
also
thank you very much.
audience participants. Thank you for joining today's lecture. And so I have to end this lecture today. So have a good day for
Thank you.
everyone.
Thank you, everyone. Bye-bye.
Bye.